Now, I first heard about Don Knuth when I was a mathematician originally, pure mathematician, and when I moved into computing, I came under the tutelage at Southampton of Professor David Barron, who Don just remembered as the editor of Software Practices and Experience for a long time, and a student of Maurice Wilkes and a great fan of tech. And Don just said he and David didn't met, but they corresponded regularly. David was a great letter writer. And I see I'm sure I see the books here. Interesting props for him. He's a true Renaissance man, computer scientist, author, historian, musician, and his life's work crosses the border of science and art. Now, looking at him there standing like a young man still, he got his Turing Award in 1974, so he must have been in short trousers when he won it. He was actually quite young by today's standards. I'm afraid, Don, today you'd probably win the ACM prize first before the Turing at that age, but clearly one of the most important people in our community. It is my great, great pleasure to welcome to the stage Donald Knuth, our 1974 Turing laureate.
Yeah, so, hey, I got it. Don't applaud, just read my books. So, she didn't mention the title of my talk this morning, and actually I don't remember the exact words of the title, but it was something like, I'm supposed to prove to you that computer science is actually a respectable discipline that has lots and lots of great results. Now, actually, that doesn't need any proof, so I don't know, why I should need any time to do it. So instead, what I want to do is tell you just a few stories, but mostly I open up for questions. So there's two microphones in the middle aisle, and after I finish my opening remarks, I plan to just answer one question after another, try to spend about 30 seconds to a minute on each one, unless there are no questions, in which case we can all enjoy a break or something. Now, okay, so in the 60s, my mathematical friend would come to me and say, "What do you do?" And I say, "Oh, computer science." "Computer science? What's that?" And at that time consisted of either artificial intelligence, numerical analysis, or programming languages. But anyway, the main thing I wanted to mention is that my colleague in Princeton told me, I'll believe that computer science is really a science as soon as it has 1,000 deep theorems. Okay, so now I don't know exactly what a deep theorem is, but it's something different than is discovered by deep learning, I think. But at the time, anyway, at the time I couldn't claim 1,000 deep results. This was late 1960s. But I think that threshold, by any definition of deep, was probably passed in the middle 70s, and now we're thousands and thousands of things. So computer science shares with mathematics the great privilege that we can invent the problems we work on. We don't have to base it on the way nature happens to have decided to go. So we can invent our own universes. We can design our own languages and our own axioms and whatever. On the other hand, computer science, I'm not sure if it'll ever be decided whether computer science is a subset of mathematics or mathematics is a subset of computer science. but I suspect that it'll actually confirm what I've always believed, is that basically there are two parallel subjects that neither one, gobbles the other, but that also there's a lot in common. Still, there's a distinct difference. I mean, it was certainly clear from the very beginning of our the computer science departments in universities that there were lots of people who could never get tenure in mathematics who could get tenure in computer science, and vice versa. In fact, probably vice versa was even more so than versa. Oh, anyway. So okay, so that was the situation when we started, and I think that's probably going to continue. That we have lots in common, but we also have this thing that we're studying things on which we have total control of what we're doing. So that makes it nice because we can actually know that we've done something when we've got a result. But a physicist can never be absolutely sure. You can't go to the sun and measure things. You can only guess. So till your dying day, you don't know exactly whether what you've done was right. But with mathematics and with computer science, we have this opportunity once in a while. Okay, now as I said, if you want to ask me any questions, please go to the microphone, and I'm going to start answering them. But while you're walking to the microphone, I want to show you something from the day that I got my Turing Award in 1974. Now, in those days, the amount of money that went with the prize was $1 million less than it is today. But I did get a very nice Tiffany bowl of silver, and my wife and I use it to serve strawberries all the time. And strawberries taste actually much better. So okay, now but what I want to show you a present that I got from my publishers on that day. So when I got the Turing Award, they presented me with these 3 beautifully bound, leather-bound volumes. I'm going to hold them up so that you can see, the gorgeous binding and everything, and look at the typesetting in those old fonts. Okay. So anyway, this was about the nicest thing I could have received at the time. I remember that when they gave them to me, though, I immediately looked inside to see the copyright page to see which printing they had chosen. Okay, so now I see people are lined up, so I'm ready to answer questions.
Hi. It's kind of a silly question, but since it's like my only opportunity to ask one of my favorite authors, I was just wondering, in the beginning of your book on algorithms, you establish a grading system for your exercises.
Yes.
And I was wondering, have you tried applying this system to other aspects of your life? For instance, would writing a grant application would be 5-1 task or a 0-0 task? Thank you.
All right, yeah. Actually, every time I look at an exercise, I have to give it another number. But what exercise did you specifically ask about?
Well, for instance, writing a grant application.
Writing a grant application.
Or 0-0. It's probably 0-0 for you, but it's more like 7-1 for me.
All right. Yeah. Okay. So that my life has been about as orthogonal to Wall Street or money and so the main reason that I was very happy to retire was that I no longer had to worry about finding. In fact, I never knew why people bought computers or paid for computers or anything. I just happened to be around where there was a computer to use. But I'm completely worthless as an advisor about anything that has to do with economics. To me, I have to admit it's a game, and I've been able to take advantage of it. Okay, next question.
Thank you very much.
Yeah.
So, I recall that when you published Tech, you published with it a very bold wager as to the number of bugs that would ever be found in it. A wager that doubled with every additional bug being found. This is the only real useful system I have ever heard of that was advertised with such a bold claim. How on earth did you do it?
So, I stopped doubling when it reached 327.68. But the beautiful thing about it was that this brought people out of the woodwork and told me about the bugs early on, and so that I now review them. I think the next time is 2021. But the bugs. There's a group of volunteers that vet reported bugs, and they file if they think it's something worthwhile for me to do, they file it away. And every once in a while, I believe in batch processing rather than swap in, swap out. So I get a batch of these requests. And at first they would be every year, and then every 2 years, and every 3 years, and so on. So the last time was, I think, 2014, and so then 7 years from then is 2021. So I'm going to look at bug reports again then. And I think last time there still was a 326.78.
The real question was, how were you able to design a real complex system with such purity that you could dare to make that wager?
Well, there's something called literate programming that helped a lot. But the full example, I wrote a paper called The Errors of Tech, which goes through and classifies exactly the first 1,500 bugs that I removed, and classifies them into I don't know, a dozen categories, and tries to figure out, was it because GoTo were harmful or something like this? And it turned out, yes, GoTo was harmful, but that was only 2% of the bug thing. Okay, so look for that paper. By the way, it was published in the journal that she mentioned, the Software Practice and Experience.
Thank you.
Sorry, I don't have any jokes, but I have two questions. First, do you think computers will become good composers of music?
Okay, so I think that I know that they're wonderful aids to composition, but some people may want to trust an algorithm to do the whole thing, but to me that's beside the point. What I like is to have a computer help me, and then I have a smaller space of possibilities to think about, and I choose the one that actually works for me.
So that's related to my second question. You've proved hundreds of theorems in your life. Do you see a role for computer-assisted theorem proving in the future?
Yes. In fact, also in the present. I mean, I've got a program running now at home that's going to help me prove one, I hope. Okay.
So you talked about 1,000 theorems as the differences between mathematics and computer science, and that made me think...
No, I didn't mean the difference. I meant, when does computer science reach maturity? Or worth consideration, right, as a subject and so on.
Thank you for that clarification. The term I've heard about social scientists is physics envy, and I wonder, and that's in respect to reproducibility and things like that. I was wondering, do you think that we have an equivalent physics envy or mathematics envy or something else in computer science, and how should we, especially as far as reproducibility of research, and how should we be addressing that?
Those are certainly good questions, but I don't think I have a particular answer for them. Certainly, reproducibility of computer results. I'm a strong advocate of literate programming, and so take a look on the web for all the things about literate programming. And I know the people in the statistical community are all embracing this because when they write their papers, they want their programs to be understandable. And so the idea of literate programming, you know, I got the idea from structured programming, which Dijkstra and Hoare and Dow wrote a magnificent book about. Three of our Turing laureates had a book called Structured Programming, and a few years later, I came up with the idea that okay, I'll have something called literate programming, so that people would have to use it, otherwise they'd be accused of writing illiterate programs. But the idea is that you don't think of a program as something that you're presenting to the machine to execute, but you're presenting to other human beings to understand. And so this is a big boost for reproducibility, I think. It comes down, we have to know how to understand programs if we're going to do anything like that. So that's, but I don't know how to. I think my own thinking process is probably different from people in other fields, and I think our field is primarily gels because a lot of people have the same peculiarity way of thinking that I have and the people in the room here, and so we discovered each other and we come together and we can talk at high bandwidth with each other. But if we have other ways of thinking, then we have to. Then I'm not the right person to really design a system for that. But I rather work in collaboration with people from other groups.
Hi, Don. Thanks for your magnificent volumes. Maybe someday you'll hatch another one. In the meantime,
Okay, yeah.
my question is, what do you consider to be the most important theorem in computer science, both from a practical and a theoretical point of view?
Yeah, that's the one question I hate the most. What is the question you hate the most, or you know, what is the?
There we go.
I mean, it's like asking a parent, you know, which of their children they like the best. But probably my favorite theorem wouldn't be one of my own. But still, I have. On the other hand, when it comes to a favorite algorithm, it turns out I do have a favorite, and that's Bob Targent's algorithm for strong components, and it's just the most gorgeous, beautiful, elegant algorithm there might be a topper for it someday, but just for sheer, I don't know. It's short, it's deep, and I use it for lots and lots of stuff. So.
Thank you.
Okay.
Hi, Don. I just wanted you to look forward a little bit. And
no. Next question.
Okay, never mind. No, so these days a lot of people are talking about the existential threats, the potential existential threats from AI and so forth.
Existential threats, okay.
Yeah, and you know, a lot of us, well, I won't put it in my opinion. A lot of us view this in a certain way, but I wondered what your thoughts were on that.
About what?
About that AI could run away and become an existential threat to us.
All right, yeah. I can go both ways on it. I can become optimistic and pessimistic, and Stuart Russell mentioned yesterday that he's spending most of his time on that, and I think he has the most sensible ideas of anybody, but it still scares me when I look at his ideas and I see that they're based on on the assumption that human beings are rational. And then I look at election results and
enough said.
That's very serious, but I'm very serious. That in other words, all of these scenarios that they're planning to say here's how we're going to keep machines from taking over is based on the fact that human beings are going to make some intelligent decisions, the people in charge, and so we have to. We have to get people who don't think like us and work with them in order to control them before we're able to control the robots.
Okay. Thanks.
Hi, Don. I'm asking my question on behalf of all future computer scientists. So based on what you know now, if you could do it all over again, your whole career, what would you do differently?
I think I would use decimal internally in tech instead of binary.
Hi, Don. You've done lots of splendid work concerning the history of our subject. But I know that you've expressed concerns about some of the recent ways in which so-called historians of science have been investigating and writing about our subject. I was wondering what you thought were the major topics, historical topics, that were worth analyzing and documenting just now, and essentially what guidance you would give to the future generation of graduate students in that subject.
Okay, I only have a minute, and I promise to answer in 30 seconds. But
You have an extra 5.
All right. Okay, so, but most of what I said is available on the web in a video called "Let's Not Dumb Down the History of Computer Science," and it's a talk that I gave in honor of Tom Kailath, who has annual lectures at Stanford. What was it, 2 or 3 years ago? And basically, I start out by saying why is history of computer science really important to people who are doing computer science? And the main reason is that we learn by osmosis if we can see what other people did, how they got their ideas, and we can watch other creative work in progress. Then that helps us understand how to do creative work ourselves. Now, but there's been a sea change in the way computer science history was done. So in the 60s, there were papers written about computer science, and it actually talked about algorithms and programming and things like that. Now, but now, if you look at the papers that are written about history of computer science, it says, here's the way somebody got funding. Here's the way somebody made a partnership with somebody else. Here's the way, or maybe somebody had problems with their parents or something like that. But they don't ever talk about anything that a non-computer scientist would not also understand. And the reason is that the whole field of history of science has changed over from what they call internal history to external history, and internal history is being played down. And one of the reasons I think is that historians now, in order to publish in journals, have to write external history. So this recent really wonderful book about the history of the ENIAC, the authors say that they couldn't have published any of that in journals of history of science. Now the universities are falling down. There isn't a single university in America that supports a computer science department that supports a historian of computer science to train the next generation. And so I'm trying to have Stanford come up at least for that. I recently read a PhD thesis that's going to be published where it's his name, Van den Hove, who studied Edgar Dijkstra's Algo 60 compiler, which, as you know, was written not in assembler but in octal machine code. And he studied it very carefully, and he makes a wonderful description of exactly the innovations in it, and the data structures and all the problems and the organization, and so on. And this is the kind of thing that I believe is what deserves to be called history of computer science.
Thank you. That's very helpful. Not least because I'm the examiner on that.
Oh, brilliant.
Okay.
I said 2 more questions. Jennifer and Alfred. I'm really sorry, guys, but we're out of time. Jennifer and Alfred.
Hi, Al.
Hi, Don. How are you? You're surviving up there fantastically. You said you were going to wing it, and look, you're winging it. So, Okay, so I have concerns, and I would guess that you might also have concerns about the lack of focus in CS education now. And I think, though I love many of the things that you have done, what I find most inspirational is the way in which you've done things, which is intense focus. So we rarely get to see you because you're always focusing and trying to get out the next volume and the next theorem and the next algorithm. I'm wondering what you would say to those much younger than us here about the way in which you approach computer science.
Okay, well, the hardest thing for me is to decide between two hypotheses. One hypothesis is that you could take anybody and teach them to be a good computer scientist, and a hypothesis that 2% of the world were born to be geeks and the other 98% were not. And depending on which way you go, now the jury is out. But let's suppose the second is true. It's not for a person who's a geek himself to understand this, but the people who measure personality also are only good at measuring the personality types of themselves. So it's very hard to actually prove it either way. But anyway, let's suppose only 2%. Then only 2% of the world is able to teach computer science. But then in a way that's going to get that they'll understand what they're teaching. So when I read in the latest communications this lack of focusing, we're supposed to teach computational thinking. What is it? And I'm thinking, it might be that the teachers are saying, I don't know how to do computational thinking myself, so how am I supposed to teach it? And that can be that to me is the nub of the problem that deserves the most emphasis. I can't go on much further. By the way, I have one more joke prepared, so I hope your question, Alfred.
I don't know. Maybe this will be general enough, Don, that you can weave your joke into the answer. I hope so. But this is kind of, I think, hopefully useful to the breadth of the ACM community. And while you're known really for mathematical computer science and really creating the field of the analysis of algorithms more than anyone else, your book is also entitled The Art of Computer Programming, and I believe your department is part of a school of engineering, as is the case for many of us here, that our schools are part of engineering. In addition, I think it's the case that our field is becoming increasingly empirical, and that we use all sorts of data science, machine learning, and other things to learn from the world around us, from the reaction of people. So I'm getting back to the point, you compared us to mathematics, and only that. Shouldn't we be compared and judged also with respect to the natural sciences as we learn from data about the world, and also the engineering sciences, because we build such remarkably complex edifices using abstraction, design, and lots of tools?
Okay, so when I gave the Turing lecture, I tried to explain what I meant by the art of computer programming, and the idea is that it's art in the sense of not in nature, as well as being beautiful. Your point is that I was comparing it only to mathematics and not to other things, and that leads to the actual joke that I prepared, because if you're
welcome.
I think tonight we're all going to get a free copy of Communication of the ACM, the latest issue. So take a look at Peter Denning's article, which is very well written, but it has a nice typo, and it calls about deep earning. Okay.
So, round of applause for a great man.